Time travel has captivated human imagination for centuries, evolving from ancient myths and legends into one of the most compelling concepts in modern science fiction. The idea of journeying through time, either to the distant past or a far-off future, strikes at the heart of our deepest desires, to correct past mistakes, relive cherished moments, or glimpse the unknown future. Across cultures and eras, time travel has surfaced in various forms. In early religious texts and mythologies, there are stories of people falling asleep only to awaken centuries later in a world they no longer recognize. For instance, in the Hindu legend of King Kukudmi, he and his daughter visit the god Brahma, only to return to Earth and discover that eons have passed in their absence. These ancient tales laid the foundation for what would become a rich exploration of time and its malleability in modern storytelling. The appeal of time travel in literature and cinema cannot be overstated. In 1895, H.G. Wells' novel The Time Machine introduced the notion of a mechanical device capable of moving through time, making the phrase time machine a part of our cultural lexicon. Wells' novel wasn't just a tale of adventure, but a deep philosophical reflection on the nature of progress, the human condition, and the inevitability of change. This story became the blueprint for countless time travel narratives in the following decades, from Mark Twain's A Connecticut Yankee in King Arthur's Court to the intricate time loops of Christopher Nolan's Interstellar. The enduring popularity of time travel in fiction reflects its intrinsic appeal. It allows us to transcend the normal limitations of life, to explore alternative realities, and to wrestle with philosophical questions about fate, free will, and the nature of time itself. But beyond fiction, the question arises, is time travel possible in reality? The concept of time travel gained serious attention in the 20th century with the development of modern physics. Albert Einstein's theory of relativity fundamentally altered our understanding of time and space. Before Einstein, time was generally thought of as an absolute, ticking away at the same rate everywhere in the universe. This view, rooted in the ideas of Sir Isaac Newton, imagined time as a constant background to the events of the cosmos, unaffected by speed, position, or gravity. However, Einstein challenged this notion with his theory of special relativity in 1905, followed by his general theory of relativity a decade later. He proposed that time, like space, was not fixed but relative. According to Einstein, time can speed up or slow down depending on how fast an object is moving or how strong the gravitational forces are around it. This phenomenon, known as time dilation, is one of the most significant discoveries in modern physics. Time dilation means that time can move at different rates for different observers, depending on their relative motion or position in a gravitational field. For example, if two clocks are synchronized and one is placed aboard a fast-moving spacecraft while the other remains on Earth, the clock on the spacecraft will tick more slowly compared to the one on the ground. This effect has been demonstrated through precise experiments, including the famous Halfel-Keating experiment in 1971, where atomic clocks were flown around the world on commercial airplanes. When the clocks were compared afterward, the one that had been in the air showed a tiny but measurable difference, running slightly slower than the one left on Earth. While this difference amounted to just nanoseconds, it provided concrete evidence that time can be altered by speed, just as Einstein predicted. While the time dilation experienced in everyday life is imperceptible, these effects become much more pronounced as speeds approach the speed of light. According to Einstein's equations, if an object were to travel at the speed of light, time would effectively stop for that object. This leads to fascinating possibilities. If humans could travel close to the speed of light in a spaceship, they could journey far into the future while only a short time passed for them. For instance, an astronaut on such a journey might experience only a few years, while thousands of years could pass on Earth. This concept of forward time travel, traveling into the future at an accelerated rate, is scientifically possible, although building a spacecraft capable of such speeds remains far beyond our current technological capabilities. In contrast to traveling to the future, the idea of traveling backward in time is far more problematic. While Einstein's theory allows for the possibility of time dilation and travel into the future, traveling into the past introduces paradoxes that challenge the very foundations of logic. One of the most famous is the grandfather paradox. Suppose someone travels back in time and prevents their grandfather from meeting their grandmother. How could they exist to go back in time in the first place? This creates a logical contradiction that has stymied philosophers and physicists alike. Theoretical physicists, including Stephen Hawking, have proposed various solutions to such paradoxes, with one being the concept of closed time-like curves, CTCs. CTCs are theoretical paths through space-time that loop back on themselves, potentially allowing for time travel to the past. However, Hawking himself was skeptical of backward time travel, famously hosting a Time Traveler's Party in 2009 and sending out invitations after the event. No time travelers showed up. Even if backward time travel were theoretically possible, the paradoxes it introduces make it extremely unlikely. Some physicists suggest that the universe might prevent such paradoxes through a principle called chronology protection, an idea proposed by Hawking himself. This principle would act as a safeguard to prevent events from unfolding in ways that could violate causality. In essence, the universe might conspire to prevent time travel to the past, thereby avoiding logical contradictions. While these philosophical and theoretical explorations are fascinating, they highlight the complexities and limitations of time travel as we understand it today. Despite the tantalizing possibilities opened by Einstein's theory of relativity, practical time travel remains a distant dream. The technological challenges are immense. Constructing a vehicle capable of traveling at near-light speeds, surviving the intense gravitational forces near black holes, or manipulating the fabric of space-time to create wormholes are all far beyond our current scientific capabilities. Nevertheless, scientific interest in time travel persists, particularly in the field of quantum mechanics. Some theories suggest that at the quantum level, particles may be able to communicate with their past selves in ways that defy our classical understanding of time. Theoretical frameworks like quantum entanglement, in which two particles remain interconnected regardless of distance, hint at the possibility that our understanding of time might be more flexible than it appears. While these ideas remain speculative, they offer glimpses into the potential for future discoveries that could radically alter our conception of time. Culturally, time travel continues to inspire creators and thinkers. From blockbuster films like The Terminator and Avengers, Endgame, which explore time travel's role in shaping human destiny, to more introspective works like Arrival and